Hello, I welcome you in this introductory video lecture on diffraction. In this picture, you see water in a pool. When the water comes through an opening in the pool wall, it diverges. The waves also behave in the similar fashion, and it is called diffraction in case of waves. These are two real examples of diffraction of light. The left one is when you see a distant light source through a long opening, and the right one is when a laser beam passes through a circular small opening. The secondary lines around the central image are the diffraction pattern. The explanation of diffraction is given by Huygens principle, which realizes the secondary wavelet theory. The phenomena of diffraction is defined as the spreading out or bending of light through the walls of obstacle it encounters while passing through a finite width aperture. It is diffraction of waves due to which we can hear the sound coming from a position hiding from our eyes. The amount of diffraction is function of wavelength of waves, which is why we can hear around corners but cannot see around them. Let us discuss the conditions for an observable interference. These conditions are already known to you, like coherence of light sources and equal amplitudes of interfering light waves. The same type of polarization is also required for amplitudes to be added or subtracted vectorially. And the last is not a too great path difference, because if path difference is too high, the coherence and equal amplitude conditions may not get fulfilled. These are the patterns by interference, this, and by diffraction, this. You see that these two patterns are similar beside a little difference, and that is why I choose to explain the conditions for observable interference in the discussion of diffraction here. Let us discuss a little more to differentiate between interference and diffraction. In Young's double-slit experiment, to demonstrate interference of light, the width of slit is infinitesimally small. If you make the slits of finite width, the pattern will change. This will be a diffraction pattern. And this is the basic difference between interference and diffraction. Therefore, the diffraction is n tend to infinite limit of interference. As it gives a specific kind of pattern on the screen, it is given a different name than the interference, instead of using similar mechanism to produce the pattern. There are few more differences, and these are: in the interference, minima are usually perfectly dark, while this is not the case for diffraction. In interference, all maxima are of same intensity, but they may have different intensity in diffraction. Fringe width could be equal in some cases in interference, while they are never equal in diffraction. In interference, interaction takes place between two separate wavefronts originating from two different coherent sources, while in diffraction, interaction takes place between secondary wavelets originating from same wavefront. Diffraction is subdivided into two classes. One, when either the source or screen or both are at finite distance from the aperture. This diffraction pattern corresponds to the Fresnel class. And the second, when both the source and the screen are at infinite distance from the slit. This corresponds to the Fraunhofer diffraction pattern. In Fresnel class of diffraction, one can observe light in the region where full darkness is expected. Here, this is the aperture and this is the light source, and this is the region where full darkness is expected, and this is the region where full light is expected. But if we magnify this region, then we see this pattern of the light intensity. Here, in the region of geometrical shadow, we can see a little intensity of light, and in the region of lightening, we can see the fluctuation of light intensity, and these are the minimas, which are non-zero minimas. In Fraunhofer class of diffraction, we see the light intensity pattern in the geometrical shadow. So these regions where full darkness is expected have a pattern of light intensity. There are few more differences between Fraunhofer diffraction and Fresnel diffraction. In Fraunhofer diffraction, source of light and screen are at infinite distance from diffracting device. In Fresnel diffraction, these distances are finite. In Fraunhofer diffraction, incident wavefront is plane wavefront, and in Fresnel diffraction, either cylindrical or spherical wavefront is used. In Fraunhofer diffraction, the diffracted light is collected by a convex lens on a screen. In Fresnel diffraction, there is no need of using any lens. In Fraunhofer diffraction, the center of diffraction is always bright, but in Fresnel diffraction, it is not the case. In Fraunhofer diffraction, single slit or double slit or a grating is used to get diffraction pattern, while in Fresnel diffraction, a zone plate is used to get the diffraction pattern. In this course, we will focus only on Fraunhofer diffraction pattern. So, in Fraunhofer class, one needs a slit to pass the light, and the slit is a very narrow aperture whose width is very small when it is compared with its length, and the light diffracts along the width of the slit. So a wave front which is plane hits the slit here, and to get a diffraction pattern on screen we use a lens of very long focal length. The lens is very close to the slit and focal length of lens is very large. Now one gets a specific type of intensity pattern at the screen depending upon how many slits are used for the diffraction. We'll discuss one by one the diffraction pattern by single slit, by double slit, and by large number of slits in the next lectures.
I hope you'll enjoy it.